Okay. Hi, everyone. Uh, my name is Zhonghan Wu, and today I want to introduce my project. My project is using hydrogen peroxide and precipitation method to synthesize cobalt oxide nanoparticles. And because the whole synthesis is in water solution and at at room temperature, so the synthesis can call green synthesis. First, I want to introduce what is the metal oxide nanoparticles. The definition of the nanoparticles is when at least one dimensional size is between 1 nanometer to 100 nanometer. The materials could call nanoparticles. And because the small size, the surface and the volume ratio is become very large, and the surface will become more important than that in a bulk material. And besides, the metal oxide is the semiconductor material, so they will cause the condensate effect. The condensate effect is means the bulk material is the continuously energy band, and they could become the discontinuously energy state. The energy state will shows the property will more like the atoms. So the due to these two reasons, the property of the nanoparticles will totally different from the bulk materials. And that's why nanoparticles can be used in many applications, such as the catalyst, bacteria, solar cell, semiconductors. And here is a diagram to tell us the metal oxide nanoparticle market prediction. It was be estimated gross to 2 billion US dollars in 2030. So the metal oxide nanoparticles is very potential materials. And today I want to introduce the synthesis method is the precipitation method. The precipitation method in general is start from the metal cations in water solution, and we adding the best carbonates or oscillates. These reagents will call precipitation reagents because they cause the precipitation. And here the precipitation could be hydroxide or the carbonates oscillate. And then the precipitation could be collect and high temperature calcine to form the metal oxide. And this method has some advantages. It's easy to operate, just adding agents, collect precipitation and high temperature calcine. And the yield could be very high because the most of the metal ions could be precipitated. And it's easy to scalable, and it's cheap, and it's green because the whole processing is at low temperature and the atmosphere, and the solid is water and using less toxic chemicals, so the processing can cause green. However, they will cause some disadvantages, such as the size distribution will become large because the nucleation and the particle growth is happening at the same time. So the distribution will become large. In this world, we want to skip the high temperature calcination is because the high temperature, they will cause the nanoparticle aggregation and sintering effects. These two effects are similar. That means at a high temperature, the particle will congregate and grows to a large particle size. And because the size of the nanoparticle is very important, the size increase, the reactivity is highly possible decrease. So we won't skip this step and just avoid the risk of the catalyst destroy. And in this world, we use the hydrogen peroxide and sodium hydroxide to produce the metal oxide precipitation directly. So we can skip the calcination. So how to produce the oxide precipitation? The oxide precipitation involve two parts, the hydrolysis and the condensation. A hydrolysis is means the metal connect with the water molecule. The electron of the oxygen will donate to the empty orbital of the metals. So the bonding between the OH will become weaker, and this proton will become more acidic, and this proton will easily release in the solution. So the proton release in the solution, this processing is called hydrolysis. And we can use the H. H is the hydrolysis ratio, means the how many protons is released in the solution to describe the hydrolysis. And here I want to introduce the 5 different forms. The alkyl is means the ligand is in water form. The hydroxyl is means the ligand is in OH form. The acyl is means the hydroxyl, not hydroxyl. The totally 2 proton is be released, only remain 1 oxygen. And the hydrolysis product will affect the following condensation and finally precipitation. So the condensation is means to produce the metal oxygen metal bridge. So they have the 2 major mechanisms, the oleation and the oscillation. Oleation is forming the OH bridge, and they will need 1 aqueous ligands, 1 hydroxyl ligands. And the oscillation is mean to need 2 hydroxyl ligands, and they will form the metal oxygen metal bridge. Here, the alkyl ligand is serve as the living good, and hydroxyl ligand can serve as the nucleophile and the living good. But in general, the acyl ligand is not involved in condensation part. So how to predict the hydrolysis product? We start from the definition of the electronegativity. The definition of the electronegativity could define as the negative chemical potential. So because it's chemical potential, so we can assume at equilibrium, each species chemical potential could be the same. And that means the electronegativity of each species will be equal. So the electronegativity of protons we can calculate from the pH value and the pure water system. And the electronegativity of the complex, we can use the partial charge model to calculate the whole complex electronegativity. This model means when the 2 different atoms binding, the electronegativity will adjust and finally reach just the average electronegativity, and the charge will distribute based on the negativity to become a partial charge. This delta means the partial charge. So we can draw the hydrolysis ratio and the pH value. How to use this diagram is interesting. We can just guess the pH 5 is here, so the hydrolysis ratio maybe is related to 1.5. That means at pH 5, the species should be actually equal to 1 and actually equal to 2. These 2 species balance. So use this diagram, we can easily know the species, the hydrolysis species at certain pH value, and that will affect the following condensation. And for this species, the charge is equal to 0. They will become the neutral. So this neutral species is possible to produce the precipitation. So this very important species. So this diagram is to predict the condensation product. It's called charge and electronegativity. The charge of the metal and the electronegativity of the metal. The empty, just the white area, means they will not produce the precipitation. Only the shadow area will produce the precipitation. And this 2 line just means the stability of the metal hydroxyl ligand stability. If they will become the white area, that means this hydroxyl ligand is not stable. There will be continued protonates or there will be deprotonates. And this XO line means the stability of the O bridge, the metal Austrian metal bridge, have to cross over this line. This format will be stable. And this line is the nucleophilic ability of the hydroxyl ligand. So only below this line, just in the area 3, the hydroxyl ligand can serve as the nucleophile. If cross over this line, this reagent, that means the hydroxyl ligand is not negative enough, so they can only be the living group. So we finally found the outside is here, the region 3. And they should happening for the ovulation and the oscillation at the same time. So this diagram can be useful to predict the final precipitation format. So in this work, we found cobalt is an interesting species. Cobalt 2 pulse, the region is at the hydroxide region, and the cobalt 3 pulse is in the oxide region. So that means if we adding the oxidation regions, we can obtain the oxide directly. And we found here is the PhD thesis from MIT. The author used the cobalt adding with the mixture of the hydrogen peroxide and the sodium hydroxide, and then finally obtain the CO3O4 oxide form. And the most interesting part is the amounts. They use very little. So my project is just based on this background, based on this method to develop. Just this in this thesis, the authors only just measure the XRD and they didn't discuss the exact mechanism and the other characterization. So it's pretty because this synthesis method is very interesting. So this is my experiment. I have 4 trials. The first one is just the control group. I only adding the sodium hydroxide. So it's cobalt none, just means no hydrogen peroxide. And the second one is the just like mimic the papers, just use the mixture of the hydrogen peroxide and the sodium hydroxide. So it's named the cobalt mix. And the 3 is adding hydrogen peroxide first and stir and stir and stir first. Here I use the wrong label. I will change later. And then adding sodium hydroxide. And number 4 is adding sodium hydroxide first. So based on it will just like produce the number 1 first, and after the number 1 precipitation appear, continue adding the hydrogen peroxide. So this is the number 4, the sodium hydroxide adding first. So this is the XRD pattern of my product. The black line is for the cobalt hydroxide. So we could see the number 1 and number 4 is including the cobalt hydroxide. And the that means but the red one is the cobalt oxide peaks. And we could find the number 2, the mixture, and adding hydrogen peroxide first will obtain the cobalt oxide. So we found, and the number 4 is a mixture of the cobalt hydroxide and the cobalt oxide. We found it's interesting that the hydrogen peroxide will continue react with the cobalt hydroxide because the 1 and the 4 compare. And there's less difference between the number 2 and number 3. That means the hydrogen peroxide maybe should react with the cobalt first and then adding the sodium hydroxide. However, the rule of the hydrogen peroxide is not clear. It's because the particle size is too small, so the XRD peaks is too broad. I need to just continue try more experimental, such as the different equilibrium of the uh, different amount of the hydrogen peroxide and different amounts of the of the, the hydrogen peroxide and the sodium hydroxide. And I need to do other characterization to understand the difference between my cobalt oxide and other papers cobalt oxide, such as the TM, FTIR, and UV. Besides the just the continue studying the cobalt oxide, I think we can still use the ligand assist to address the morphology of the nanoparticles. In previously, in previous, our group has published used the lactic acid to address the morphology of the cereal oxide. So, is it possible also possible work in cobalt oxide? Or we can try other ligands. The ligands will change the hydrolysis product and the condensation parts. So the finally morphology will be different. And the other part is we can more detailedly discuss the mechanism. Because the hydrogen peroxide seems can work with the cobalt hydroxide. So I just guess is that other mechanism involved in the formation of the cobalt oxide. Because the hydrogen peroxide is easy decomposition happening in basic solution. So they maybe produce the radicals, and radicals maybe involve the metal oxide formation. And this paper is mentioned that the cobalt can serve as the sensor for the hydrogen peroxide to produce the hydroxyl radicals. So that means the radicals can maybe possible exist in the solution, and maybe the radicals is the key part of the synthesis. And besides the mechanism discussion, here is a paper. They just use the cobalt precursor and adding this potassium persulfate. This persulfate is like hydrogen peroxide. They have the OO, the OO bridge. It's unstable. So, and they use the UV light of the sunlight, and they finally can obtain the nanoparticles. They didn't adding any bass. So they, is that possible? I use the UV light to improve the synthesis of the cobalt oxide. This is the other following topic. So today I introduced the formation of the metal oxide. They generally can involve two parts, the hydrolysis and the condensation. And the hydrolysis ratio vs this pH diagram can tell us the hydrolysis product, and the charge electronegativity diagram can tell us the precipitation format. And for my experiment, we can synthesize the cobalt oxide via the hydrogen peroxide. It's just following our prediction. The cobalt is oxidized to sulfate, so we obtain the sulfate, the oxide form. But the rule of the hydrogen peroxide is still unclear, and I still need to do more experiment to to explore the mechanism. And the following topic, like the ligand assist and the UV improvement, should be also considered. So this is today's precipitation.